Hello, I welcome you all in this presentation related to the subject materials processing fundamentals and practical. And we are talking about the various practicals and lab demonstrations related with this course on material processing. In this particular presentation, I will be talking about the shielded metal arc welding of the steels and the kind of microstructure which is developed in the weld zone as well as in the heat affected zone, and the mechanical properties that are obtained as a result of the development of weld joint by SMAW. So, as far as content is concerned, we will be talking about the various aspects. Like objective of this practical is to learn about the following, like what are the different systems related to the SMAW process, then on what basis we choose the electrode based on the thickness of the plate to be welded, and then how do we identify or designate the welding electrodes we used in SMAW according to the American Welding Society or according to the BIS, Bureau of Indian Standard. And then we will see in the demonstration of the welding where we will actually be showing the how welding is performed. Thereafter, the weld joint whatever was prepared using a SMAW was samples were taken, then the transfer section was prepared to study the microstructure and then mechanical properties. So, these were the different things as far as the practical related with the of SMAW process, shielded metal arc welding process of the steel. Okay. So, in as far as the system components are concerned, we for SMAW we use basically the welding transformer. Okay, welding transformer which converts the high voltage. You see, we normally get the supply of the high voltage and low current. Welding transformer converts this kind of the domestic supply into the low voltage and high current, and this is used for supplying the desired power for welding. The heat generated during the welding is found a function of arc voltage and the welding current being used. Depending upon the welding speed, we get the particular net heat input, which facilitates the melting of fixing surfaces for development of the joints. So, Vi by S gives us the net heat input, and if you multiply by the thermal efficiency, the net amount of the heat which is being transferred. So, that helps us to get the net heat being delivered. So, the welding current and the arc voltage, these are the two, V and I are the two important aspects. Okay. So, here what we have, like the welding power is connected through the cables to the electrode holder, and then we have, say this is the electrode holder and this is the electrode. Electrode here is coated. This coating provides, after thermal decomposition, this coating provides the desired, it performs multiple functions, like helps in striking the arc easily. In thermal combustion of the coating provides the inactive shielding gases for protecting the weld fluid from the atmospheric gases. It also helps in removing the impurities by forming slag. It also helps in adding the alloying elements. So, there are multiple functions. So, coating is one of the major factor or major aspect as far as the SMAW electrode is concerned. Like arc is struck between the base metal and to be joined and the electrode, and heat generated facilitates the melting. Then by thermal decomposition of the coating, inactive gases are generated. Another terminal is connected to the base metal. So, usually we use the AC for you see, welding transformer supplies the AC current, that is the one of the most common use, but welding transformers can also supply DC. Depending upon the type of electrode, we can use suitable AC or the DC for development of the weld joint by SMAW process. Okay. So, electrode is one of the most important aspect as far as the SMAW is concerned. So, this electrode is designated in different ways according to the different standards. So, this designation according to the American Welding Society contains E6013. Okay, say this is one typical electrode. E stands for the extruded electrode. Okay, 60, this indicates the minimum strength of the electrode that should be offered by this electrode is 60 KSI. Okay, so the first two digits show the minimum strength in KSI. Third digit shows the welding position, and the last digit indicates the current, type of current AC DC, or the type of coating which is associated with the electrode like rutile, basic, cellulosic. So, depending upon the type of the coating. So, these are the main constituents related with the AWS electrode designation. Okay. So, it you see it is indicated like E, these 4 digits. So, the first E, as I have said, it is extruded electrode. B, and then the first two letters show the minimum strength, and sometimes the designation contains the 5 numbers. So, in that case first 3 numbers indicates the minimum strength. Say it may be like this. So, 100, 1, 3. Okay. So, 100 will indicate the minimum strength is 100 KSI. Okay. Then the fourth digit becomes the welding position, and the last digit becomes the last digit shows the current and the type of coating. Okay. So, the third digit welding position, fourth digit type of coating and type of current. What is the meaning of this? Welding position means if there is a like 6013. So, 1 indicates all position electrode, which means this electrode can be used for flat, horizontal, vertical and overhead. If it is 2 like 7023, which means it is flat, it can, this electrode can be used, 2 means it can be used in flat and horizontal position. If it is 337032 means it can be used only in the flat position. If it is 4, then flat, vertical, horizontal, vertical down, overhead positions. Okay. So, this is what I have said, like if there are just 4 digits, then first 2 digits indicate the minimum strength. Here it says 60, which means 60 KSI, and if there are if there are 5 digits in designation, then first 3 digits indicates the minimum strength in terms of like say the first 3 digit indicates the minimum strength of the electrode. As far as the fourth digit is concerned, like fourth digit can range from like say 1 to 8, and each number indicates the unique electrode coating and the type of current to be used. Say 0 means 6010 means minimum strength is 60. The welding position, it is for all position welding, and 0 indicates it is a high cellulosic electrode with the DC positive. That is the electrode polarity. So, this also we say as the DCEP, electrode positive, or DCRP, reverse polarity. Okay, for the positive. When if it is DC negative means it is DCSP. Okay, or the EN, electrode negative. So, if we have the number 1, then high cellulosic potassium, AC, DC positive and DC negative, and if it is 2, then high titanium sodium electrode, and it can be used with the AC or DC negative. For 3, so likewise we have the one unique number for a particular type of the coating and the type of current to be, corresponding current to be used for the welding purpose. Okay. So, this is about the AWS electrode designation approach. As far as the BIS electrode designation method is concerned, it contains 6 digits and 1 letter, like the E is about the extruded electrode, then there are 3 digits showing the different things, then say here 3 to 5. So, the first digit shows the type of electrode coating, second digit shows the welding position, third digit shows the current, type of current and its magnitude to be used, then set of 3 digits shows the minimum strength and the set of mechanical properties that is attainable. So, say 411 means it is the strength, minimum tensile strength is say can range from say 410 to 510, and the corresponding yield strengths and the minimum elongation that will be offered by these electrodes, and the corresponding and the temperature corresponding to the minimum toughness of 47 joule. What is that minimum temperature at which the electrode will be offering the minimum 47 joule of the toughness? Okay. So, our BIS electrode designation contains the a set of 3 digits, 6 digits. First 3 digits indicate the type of coating, welding position and the type of current. And then the set of last 3 digits indicate the minimum tensile strength that it can offer apart from the combination of other other mechanical properties like yield strength, elongation and the impact toughness. The last character, which is a letter, which indicates like if our electrode is say H, then it will indicate hydrogen control. If it is J, then iron powder, it is having iron powder with the metal recovery of 110 to 130%, K for iron powder added in the coating with the metal recovery of 130 to 150, and likewise for more than recovery of the iron powder with the metal recovery more than 150%. P is used for the deep penetration. So, these are like special characteristics related with the electrodes. Okay. If that is there, then we will be using these additional letters at the end. Okay. Now, as for SMAW, what we need basically one welding transformer, one electrode and the suitable welding plates, suitable metallic plates for the welding purpose and the hammer for peening, so that the flux which is forming slag is removed. For removing the slag as well as the relieving the residual stresses, okay, this the peening hammer is used. So, but when we have got say the plates like this, if the thickness is less than 5 mm, then even square edge preparation is fine. But if the plate thickness is greater than 5 mm, then depending upon the thickness for butt welding, the grooves are prepared in different ways. Okay, like say single V, single U, a single bevel like this, or single J like this. So, J, V, U or bevel, these are the kind of the groove edge preparations for developing the butt joints. Okay. When the thickness is more than 5, but say maybe around 10 mm, but if the thickness is further greater, then what we do, we go for the double edge preparations like double V like this, double U like this and the double bevel or the double J this manner. So, the double groove preparations are used for further greater thicknesses, which offer many benefits in terms of the volume of the weld metal to be deposited, in terms of the residual stress and distortion control. So, in the following section, now we will be seeing the different types of the joint designs which are used. Say up to 6 mm thickness, we can use directly the square groove edge preparation. So, it does not require any edge preparation, our edges must be square and clean, and the gap between the plates can be 1.5 to 3 mm. Then we can have the single V, single U, then double V, W, single bevel or single J, double bevel or double J like this. So, depending upon the thickness, we can use the different types of the edge preparations. When we for greater thicknesses, we go for the double V, double U, double bevel, double J kind of the arrangements, because that helps in reducing the weld metal volume which is deposited. It helps in reducing the residual stresses, because the residual stresses being developed during the welding on each side will be balancing each other, and that also helps in reducing the distortion tendency, and these factors in turn help in increasing the welding speed as well as increasing the productivity. Whatever the weld joint using the by the SMAW welding is developed like this. Okay, this needs to be prepared for the study. So, what we do, say the top view is like this. So, what we do, this is the weld line. So, we take transverse section like this. When transverse section is cut, we get the arrangement or the transverse section, the in front view, we are able to see the transverse section like this. Now, this transverse section is prepared. How it is prepared? After cutting, we have to do the grinding, then polishing and then etching. Okay. After grinding, polishing and etching, what we do? So, the preparation of samples by polishing, first grinding, then polishing, then etching. For this is done for the hardness testing as well as for the microscopy, optical microscopy. So, optical microscopy is performed to capture the micro structure of the welded transverse section of the joint, and then hardness profile of the weld joint is developed. Now, we will see that how the actual the welding systems look like and how the welding is performed in the following section. Hello students, in this practical demonstration we will be talking about the shielded metal arc welding process, and later on we will see the demonstration of this process. You know, this process is based on the very simple principle of using the heat being generated by the electric arc, and that arc heat is used for, like say, melting the edges of the plates. Like these are the two steel plates, so these are to be fused. These are to be fused in order to have the metallic continuity along the weld line. So, to develop the arc, so the most important thing here is to develop the arc so that heat can be generated in a very controlled way in order to realize the true thickness penetration during the welding. So, how the arc is generated? Like say there is a power source for shielded metal arc welding. Mostly we use the transformers for AC, and the rectifiers and the generators for the DC welding. Each one will have its own capacity. This particular transformer has got a rating, say, from 25 to 300 ampere. So, depending upon the thickness of the sheet, we set the welding process for the different current values, so that the same will be supplied through the arc to the workpiece for closing the circuit, so that arc can be established. So, here you can see there is a transformer and there are different control panels, and here there is a cable through which the power is being fed. This is the electrode holder, which is very easy to hold and unhold the electrode at a particular angle. Okay, since it uses the replaceable electrodes, electrodes will have the limited length of, say, 300 or 400 mm. So, these are consumed in process of the shielded metal arc welding, and here you see if this electrode, so this is the electrode holder is connected with the cable to feed the power supply, and here you see this is the electrode. Inside there is a core wire. This is mostly made of the metal composition as per the base metal which is to be welded, or any other composition for the special requirements. So, this is diameter of this the wire which is further covered with the coating or the flux. So, we call it diameter of this wire is termed, this is called core wire, and its diameter indicates the electrode size. It may be 3.15 or at 4 or 5 as per the heat to be generated to weld the plates of the different thicknesses. So, thickness of the plate primarily dictates the electrode to be used, and that in turn dictates the kind of the current to be used for the welding purpose. And you know that this is the coating of the flux which plays a number of roles. For the first and foremost is like the easy arc initiation, then this the flux decomposes during the welding and provides the effective shielding to the molten metal, so that the sound weld is developed, which is free from the inclusions and the defects. So, here so during the welding very intense heat is generated, and that generates a lot of harmful radiations are also generated during the arc welding. So, it is very important to protect the eyes. So, for protecting the eyes, a face shield of this kind can be used, or goggles are also there for the protection purpose, so that you can easily handle the arc as well as you can control the the arc and the weld pool as per the need. Apart from these two things, there is also, you can say, the hammer. This is called chipping hammer, which is used to remove the like the slag which has been developed after the welding over the plates. So, you can see the number of electrodes are there because these are consumed in process. So, indirectly say this is also consumable type of the arc welding, where electrode itself is consumed. Electrode plays the two roles here. It helps in establishing the welding arc, one. At the same time, the melting of the electrode facilitates the feeding of the molten metal to the weld pool for the development of the weld joint. So, this is one of the most common welding process in most of the repair shop and workshop. This kind of the welding is performed because of the two reasons. One, it is very easy to do, easy to control over the molten metal, and the kind of the power transformers which are used, they are also very cost effective. So, nowadays you can see they are very light in weight, maybe 10 kg, 15 kg. So, you can easily transport from one place to another. Certainly, you need the domestic power supply for the purpose of establishing the welding arc, so that you can provide the required power during the welding. So, in SMAW process, you know that the arc has to be established, and the arc is established whenever the circuit is completed. So, the one terminal of the transformer is connected to the electrode and the another one is connected to the work table on which the plate to be joined. So, the terminal which is connected to the work table is known as the ground connection, and position of that ground connection we can choose as per the requirement to avoid the arc blow kind of thing, or it can be placed at any other convenient position. So, basically the one terminal is connected to the electrode holder and another one is connected to the work table, so that the circuit is completed when arc welding is performed. So, shielded metal arc welding is one type of the fusion welding process, where the sufficient heat should be generated in order to fuse the plates or the sections to be joined, and the heat generated depends upon primarily on the welding current being supplied. So, depending upon the thickness of the sheet to be joined, you can see for 1.6 mm, for 3 mm, for 6 mm and for 9 mm and 12 mm or above. Like say the plates of the different thicknesses are to be joined, then we need to use the different current values, because thicker the plate, greater the heat required, and that can be generated through the simple formulation of like VI, welding current, and the voltage. So, the voltage is by and large fixed, maybe 30, 40 or 50 depending upon the kind of electrode, but the current is adjusted as per the need of the heat to be generated for welding of joining or welding of the given thick plate. And for as per the thickness of the plate, we need to select the suitable current, and as per the current setting that we need, we choose the suitable electrode size. So, if you can see 1.6 mm, 2.5 on the different electrodes for the different current rating. If you see, this comes out to be around 35 to 40 times of the electrode diameter. Okay. So, this is indicating electrode diameter, which is primarily the core wire of the electrode, not the diameter of the electrode with the flux. Okay. This is another way of representing the electrode of the different sizes. So, now we will show you the demonstration of the shielded metal arc welding process and how do we do it procedurally. Okay. So, for developing the shielded metal arc weld joint, first of all we have to strike the arc. So, to strike the arc, electrode is touched at elsewhere, so that there is a completion of circuit and arc is established. Then arc is moved towards the plates which are to be joined. So, to maintain that the plates to be joined are kept in particular position and spacing, we do the tack welding. So, the tack welding is being done at the top as well as at the bottom. Okay. So, this will help to retain the two plates to be joined in a particular position, so that they do not go out of position. So, this is like the tack welding on the bottom side is being done. Okay. So, this is how do we move the arc towards the location where heat is to be applied. Okay. This is the tagging process, tack welding process. So, where we try to maintain that arc. Now, this is the welding process only. So, here in very controlled way, the arc is being moved along the weld line, so that there is a proper deposition of the molten metal as well as the through thickness penetration is also realized. The process is quite fast, but it requires a lot of skill in order to manipulate the arc, control speed and the movement of the arc, and avoid the sticking of the electrode with the workpiece. So, the welding current and the speed of the movement of arc determines the amount of heat being supplied during the welding. Okay. So, this is how you can see the weld is done, and here we have replaced the electrode, and again the welding will be continued where from it was left. Okay. So, this is one of the drawbacks also of the shielded metal arc welding, where we use the electrode of a particular length. Once it is consumed, we have to stop the process, and again the electrode, a new electrode is used. So, this brings in the little discontinuity or breakage in the welding. So, we may find that the location where from the next electrode has been used for the welding purpose, that may be full of the discontinuities also. So, now we can see that whatever the slag has been deposited, that we can take off using the chipping hammer. Okay. This is very important. Especially it is important in case of the multi-pass welding, because if it is not removed, then it can be retained there as a inclusion. Okay. So, this is how we can see the shielded metal arc weld joint can be developed using the arc welding. Like say if the weld joint has been developed and say and transverse section has been prepared like this, okay, and then we try to study its weld thermal cycles at point 1, point 2 and point 3. So, at 3 the temperature will be maximum, cooling rate will be high. At point 1 it will be little lesser and cooling rate will be lesser, and at point 3 it will be further lower. So, if we see point 3, which is in the weld zone, will be offering the highest heating rate and cooling rate. On the other hand, point 2 or point 1, which is next to the fusion boundary, will be experiencing little lesser heating rate, cooling rate and lesser peak temperature. So, this variation in temperature as a function of time is known as weld thermal cycle. So, all the zones during the welding of steel which are heated above the lower critical temperature, that is lower critical temperature, say 727 degrees centigrade. Whatever the zones are heated, say if the zone 1 or zone 2 are heated above the lower critical temperature, then they will be experiencing, these zones will be experiencing the austenitization, maybe partial or full. So, if it is heated above the upper critical temperature, then it will be heated to the completely austenitic state. And if a particular zone is heated to the intercritical range, means above the upper critical temperature, but above the lower critical temperature, but below the upper critical temperature, then will be in intercritical temperature zone. So, if we see all the regions which are very close to the fusion boundary will be heated at higher temperature for longer time as compared to those which are away. Okay. So, the zone which is very close to the fusion boundary will be experiencing higher temperature for longer time as compared to those zones which are away. So, because of this high temperature exposure for a longer time, we get the coarse grain structure. So, we get the coarse grain HAZ, while those zones which are heated above the lower critical temperature, but below the upper critical temperature, like in intercritical temperature zone, that will be experiencing the partial transformation of perlite into the partial austenitic state, where alpha plus perlite which is there in room temperature. So, perlite will transform into the austenite, while part of the alpha or ferrite will be transforming into the austenite. So, we will be having partially transferred ferrite into the austenite plus austenite. So, this partially transferred austenite, so whatever the alpha has transferred into the transformed into the austenite, that will be available for further transformation into the other phases as per the cooling rate. Okay. So, let us see, say particular 0.3% carbon steel during the welding when it is heated in the intercritical zone. So, in at this temperature, what it will have? Perlite transformed completely into the austenite at just above the lower critical temperature, and whatever part of the austenite will be part of the ferrite will be transforming into the austenite. So, this zone will have both ferrite plus austenite. Okay. Now, later on when cooling happens, the faster cooling, what it will be resulting in, the ferrite will remain as it is, while the austenite will be forming the fine perlite. So, what we get basically the fine ferrite plus fine perlite, and as a result of this we get a zone of the coarse grained HAZ next to the fusion boundary and fine grained HAZ little away from the fusion boundary. This is the zone which will be experiencing the heating in the intercritical temperature range, and this is the zone which will be experiencing the temperature above the upper critical temperature. So, all the zones which are heated above the upper critical temperature, those zones experience the greater grain coarsening and they result in the coarse grained heat affected zone, and those zones which experience the temperature in the intercritical temperature range, then they will be producing the fine grained heat affected zone. Okay. So, and further away the zones which are heated below the lower critical temperature, they will remain in the ferritic and perlitic state, and no major microstructural change will be experienced in those zones. And that is why what we get, the coarse grained HAZ, fine grained HAZ and base metal. Okay. So, this is the zone which will be heated to the lower critical temperature, this is the zone which will be heated up to the upper critical temperature, and then this will be the up to the melting point. So, these are the three. So, the zones next to the fusion boundary is heated up to the melting point, then we have upper critical temperature and then lower critical temperature. Okay. So, this is why we get the coarse grained heat affected zone, fine grained heat affected zone, and then the base metal. This is just one aspect about the grain size. The zones which are next to the fusion boundary, has been heated to the too high temperature in fully austenitic state. When experience high cooling rate, what they result in? They result in simple austenite transformation into the martensite because of this rapid cooling, and therefore, the zones next to the fusion boundary and in the fusion boundary we invariably get the martensite, here also martensite, and then martensite plus perlite, and then fine alpha plus perlite, like this. So, if we try to see the structure corresponding to these zones, this is the base metal. Okay. This is the base metal, and if you see the coarse grained heat affected zone, this is the partially refined HAZ, this is fine grained HAZ, and this is the coarse grained HAZ, coarse grained HAZ. Okay. So, if we see these four zones, this is the base metal, this is the base metal, this is the partially refined zone, then refined zone, this one, and then coarse grained heat affected zone. So, the next to the fusion boundary we have coarse grained heat affected zone, then little away from that we have fine grained heat affected zone, then partially refined HZ, and then the base metal. These are the 4 different zones. And next to the fusion boundary, due to the higher cooling rate and formation of the coarse grained austenite, we get the martensite structure, which is coarse coupled with the pearlite. Okay. And these structural changes in general, what they produce, like say this is the weld zone. So, on measuring the hardness distribution from the weld center away from the weld center towards the base metal, what we find, hardness of the weld zone is maximum, then it is little, it is coming down. Okay. So, this is a zone which will be experiencing the martensitic transformation completely. Partial transformation into the martensite will be there in the heat affected zone, and then fine grained, and then base metal. Okay. So, this higher hardness of the weld zone and of the heat affected zone is basically attributed to the martensitic transformation due to the heating to the higher temperature coupled with the higher cooling rates. Now, I will summarize this presentation. In this presentation, basically talked about the different system components related with the SMAW, how to designate the electrode, and when a weld joint by SMAW of the carbon steel is developed, how the different types of the microstructural features are produced in the weld zone as well as the heat affected zone. Thank you for your attention.